Hey, I'm Austin Rowland, and this is my Physics 2 Lab 4 video report on DC and RC circuits. So the purpose of this lab was to use a circuit simulator to predict behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of conventional current and potential difference, and examine the behavior of ohmic resistors and capacitors. Some of the results from this experiment include calculating our RC time constant, which was 5.98 seconds, the current in I1 and I2 locations, which was 0.02 amps, and the charge and discharge times for a 10 ohm light bulb and a 20 ohm light bulb. So for our series circuit using the ammeter readings, so we had two batteries that were 3 volts in total. We had two resistors at 47 ohms and 100 ohms. The readings in these ammeters we predicted using Ohm's law, which gave us this value of 0.0204 amps, while the actual value was 0.02, and this was due to the rounding on the ammeter. When we flip the ammeter reading becomes negative, and ammeters do not affect circuit resistance, which was verified in our results. Using voltmeters in a series circuit. So a voltmeter has infinite resistance that halts the flow of electrons. It reads potential difference across the circuit, which was 3 volts due to the batteries. Our current reaches 0 amps as the circuit is completed by the voltmeter, which has an infinite resistance. And if the voltmeter were wired in parallel rather than in series, the circuit would be unaffected, and we will talk about this in one of the later slides. So measuring current and voltage in a series circuit. So here we had our potential differences set up on the left. So the naming convention for these was the positive terminal on the left, negative terminal on the right. And here we can see that for 8 different locations on the circuit, our current reading was the same no matter what, because it was the same at all locations because we were using a series circuit. And the potential differences measured at each set of points sum to 0, and this is stated by the loop rule. We can see that over here because we have -3 and our positive potential differences sum to 3, and those cancel out and give us 0. So this is our potential versus position graph. So this gives us the potential at each location on the circuit, in which you can kind of also look at potential difference. So parallel placements on the circuit for the ammeter and voltmeter. When you place the ammeter in parallel, it creates an additional path of 0 resistance. Current increases because electrons flow through the path of least resistance, which avoids that 100 ohm resistor, which decreases our total resistance. And we can calculate our new current through Ohm's law, and it comes out to be 0.0638 amps. And when we place the voltmeter in parallel, it does not change the current as electrons do not flow through this path, and it creates this additional path of infinite resistance, which is why those electrons do not flow through the path, because it always chooses the path of least resistance. We can use our results from the series circuit to calculate these resistances for different circuit components. So we verified that our resistors are 47 ohms and 100 ohms using the potential difference at those locations divided by the current. And we also verify that the resistance of the wire and resistance of the ammeter are equal to 0 ohms as they should be. Next up is our RC circuit. So this includes a battery, a light bulb, and a capacitor. So as the capacitor charges, the bulb turns on and then gets dimmer as it turns off. As the capacitor is discharging, the bulb will turn on and then get dimmer until it turns off again. So while we're charging, the current is flowing through the bulb, and it flows until it reaches the capacitor where it's going to stop flowing, and the current slows until it completely stops flowing in the circuit and the capacitor is completely charged. And then while we're discharging, the current is flowing through the opposite direction and is once again slowing until the current reaches 0 on the other end. So we can test this by using a different, resistance bulbs, and we used a 200 millifarad capacitor for this. So we can see that our charge and discharge times for the 10 ohm bulb are around the same, and you can verify it using the voltmeter to check that it has completely charged and discharged. And same for the 20 ohm bulb. They're about the same amount of time for each of those. So with our RC time constant, we're going to set up a similar experiment to what we did for this. We're going to set up a discharge experiment with a 30 ohm bulb, and then we're going to measure from each second interval from 0 to 20, and we're going to get the voltage, and then we're going to divide that by the initial, which is 9 volts. Then we're going to grab the natural log of all of that, and that'll be equal to 1 over our RC. So once we calculate this using a line of best fit to calculate what that ln of V current divided by V initial looks like, we can divide 1 by that value we obtained to obtain the time constant, which in this case was 5.98 seconds. And 2 questions for consideration. So what if you were doing this lab in real life and using an actual ammeter instead of a simulated one? So we would have slightly different values because of all the infinite and zero resistance assumptions used in this lab. These values are either very high or very low, so they do not significantly affect our answer enough to worry about them. And what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in our circuit? It would become charged almost instantaneously. It would not become charged instantly due to the small resistance of the wire and battery. However, it becomes charged instantaneously because it essentially functions as having zero resistance. This is the end of my lab. Thank you for watching.